So today I'll be talking about my work on rethinking client-side caching for the mobile web. And this is a joint work with my colleague Vaspal and advisor Harsha Madhyasta from University of Michigan and Ravi Netravalli from UCLA. So newsflash, mobile web is dominant in the last couple of days, years, and especially the last decade. We've been seeing a moving trend of how people have been accessing the internet more and more using their mobile phones. And given this trend, we've been making a very common observation in the past couple of years that despite being dominant, it is still slow. And I would just like to quote some of the most large-scale studies that I know of date. Keynote Systems analyzed thousands of pages, retail sites specifically, and noted that they take as much as up to 10 seconds to load median mobile web pages. And Google conducted a much larger study, which involved around 11 million web pages on a variety of different mobile devices and network conditions, and made the observation that around 70% of them were taking greater than 5 seconds before anything even appeared. Apart from just poor performance, which essentially causes a very high dropout rate, people are likely to bounce and abandon websites if they are slow. A very strong detrimental impact of slow web pages is the way it negatively impacts revenue. And this is of a very high concern to big tech companies. So for example, Amazon conducted this large-scale study to estimate how much of an impact even a second of delay in their services would cost, which, as you can see from the title, can mount up to $1.6 billion. So having established this problem, let's kind of like take a step back and dive deep into why mobile web pages have been slow. There has been a ton of work in the past decade, and an interesting work came out from 2011 HotMobile paper, which did a very thorough study of why mobile pages at that time were slow. And the two big reasons they pointed out were slow network. So the network bandwidth was poor and the round trip time latencies was high. And second, this notion of serial HTTP requests. So there was not really a notion of HTTP pipelining. HTTP1 was the predominant protocol at the time, and you didn't have the option to send all the network requests parallelly at the same time. However, in the last decade, a lot has changed. A decade is a very big period of time, especially in the mobile landscape. I'd like to point out the three main trends that has caused the shift from network no longer being the problem, basically. First, there has been a significant increase in the amount of JavaScript that most of these web pages execute. Secondly, the network speed has significantly improved, both in terms of bandwidth and round trip time latencies. And finally, there have been newer protocols around HTTP2 and more recently HTTP 3.0. These support features like server push, no limits on the number of TCP connections that can be created with a web server, which essentially help clients create more parallel connections and therefore send requests in parallel, essentially elevating both the concerns that were highlighted about a decade ago. So given these trends, lately, the shift has come from network to computation being the bigger bottleneck for mobile web performance. And in order to better understand this, we conducted a small experiment. In our experiment in the corpus, we considered the landing pages of Alexa top 1,000 sites. We loaded these web pages in a controlled setting such that all the content was locally cached, thereby eliminating any network-induced delay. And the observation that we made was that around 9% of the pages had a page load time of greater than 3 seconds. The reason we were looking at 3 seconds as a number was because prior studies have highlighted that this is basically the amount of time up till which the user is willing to wait for the page to load, and beyond which the bounce rate would increase and the user is likely to abandon the page. Another trend that we notice from a computation point of view is that clearly the computation prowess of flagship phones has been increasing every year, more so in the developed regions. However, this mostly comes from increasing number of cores. So in the past 5 years, flagship phones for Samsung, Google have increased the number of cores from 4 to 8, and more recently 16. However, this increasing number of cores does not really improve web page performance that much. So we conducted a small experiment with only those sites that were taking, so we eliminated all the network from the page loading pipeline, and we were just focusing on compute. And we loaded those websites with and without all the cores in the phone being enabled. So 8 cores versus only 4 cores. And as you can see, it has a very little impact on the page load time performance. Why is that the case? So I've been talking about how client-side computation has seemingly become the bottleneck. So when I talk about client-side computation, there is a lot of different things going on the client side. At a high level, these can be broken down into JavaScript execution, compiling, painting, loading, and rendering. We focus our analysis on those sites which were taking greater than 3 seconds. And we break down this computation time for all of them. And for the median page, we noted that JavaScript execution is significantly dominating these delays. As you can see from this pie chart, around 69% of the total time was accounted for by only JavaScript execution. And this partially explains that previous graph that I showed. The increasing number of cores does very little in terms of improving performance because JavaScript is inherently single-threaded and cannot really leverage different cores on a device. So having made this observation that computation is a bottleneck, client-side computation, we are not the first ones to have made this observation. There has been quite a lot of prior work. And I'll talk about some, at a high level, 2 lines of solution, a proxy-based approach and a server-side solution to optimize the amount of computation a client has to do. So let's look at the first line of solution, which the idea here is that the client would offload the page loading process to a proxy. So here is a client which is trying to fetch a web page, cnn.com, but instead of talking to the origin web server, it's talking to a man-in-the-middle proxy. The man-in-the-middle proxy is making the web request on client's behalf. It loads the web page, and finally it ships back either a processed version of the web page or an optimized version of a web page, which hopefully the client can apply and accelerate the page load process. The shortcoming of this technique is severe privacy implications. Modern web pages are highly dynamic and customizable, and therefore, in order to make sure that the web page is accurate, you would have to share cookies, maybe even client-side state with the proxy. Secondly, HTTP integrity would have to be compromised so that the man-in-the-middle proxy can basically look at the raw content. Let's look at the second line of solutions where we get rid of the proxy. And now servers do that pre-processing for us. So the client is again talking to the origin web server to get back some response. Instead of simply responding with the network responses, the origin web server is doing some pre-processing on its end. It again generates the web page and some processed version of that and ships that back to the client. And then the client can apply that locally and hopefully accelerate the page load. This line of solution also suffers from a similar problem. It is inherently unaware of client-side state, so it risks the possibility of sending back an incorrect version of the page. Simultaneously, for this solution to be really feasible, a lot of different servers will have to adopt the solution because a single client is talking to a lot of different origin servers. Finally, both these lines of solution have a problem of requiring non-trivial amount of computation resources, because either the proxy or the web server will have to do this pre-processing for every web page that every client visits. So in this talk, I'll be focusing on 3 things. The first thing is the proposal. We advocate for a purely client-side solution. And in our client-side solution, we are proposing using a JavaScript-based execution cache. The idea here is basically JavaScript-based memoization. How do you memorize JavaScript execution and reuse it? Then I'll talk about the potential benefits that we can get with this JavaScript-based execution cache. And finally, I'll end the talk with some high-level challenges that need to be overcome in order to realize this vision. So the key idea behind this proposal is to exploit this temporal locality, which web pages already do from a network standpoint. So most browsers come with network cache, so as to reuse the same, so as to not fetch the same network request over and over again. The idea is to do something similar, however, for JavaScript execution. Most users are likely to visit the same web page over and over again, and therefore there is a possibility that future visits to the same page might execute same JavaScript. And the idea here is to reuse executions from prior visits to skip certain JavaScript executions from the current visit so as to speed up the web page load. So let's walk through a high-level flow of how this computation cache would work in practice. On the left-hand side, you can see this is the traditional browser cache, which has a traditional browser, which has a network cache. And now it's augmented with this compute cache. The client browser talks over the internet, tries to fetch some web resources. Once it's done loading the pages, simultaneously, it will end up storing some JavaScript files in the network cache. Now onward, we propose that the browser essentially rewrites these files so as to make these files capable of generating computation cache and simultaneously storing computation cache. Now, when the user revisits the same site again, it will fetch some of the resources over the network, and simultaneously it will fetch some of the resources from the cache, which this time are modified. Upon executing these modified resources, the client browser is now capable of generating this computation cache, which it stores in its browser cache. Now, when the client visits the same site again, it will not only leverage the network cache, which it traditionally does, but it will also use this computation cache to skip certain JavaScript executions during the page load, and as a result, accelerate the page load process. What's interesting is that all of these three phases are happening at the same time for every load, because for every load, new JavaScript files are being dumped into the cache and old JavaScript files are being purged from the cache, and simultaneously new computation cache is being created and purged. Now, two natural questions are what really goes inside this computation cache and how do we capture this computation cache? Let's look at the first question. There are very different granularities at which these computation cache can be created. You can have a single cache entry for the entire web page. You can have cache entries for each JavaScript file. What we realized was that the function level granularity is the most optimal granularity here for multiple reasons. First, most of the JavaScript code resides inside JavaScript functions. So for the median page in our corpus of websites, which is landing pages of Alexa top 1,000 sites, we notice that 96% of code resides inside JavaScript code and resides inside JavaScript functions, my bad. And therefore, with this granularity, we propose that there would be a cache entry for every invocation of every JavaScript function that gets executed during a page load process. And this cache would essentially consist of all the state that is accessed by a JavaScript function. So let's look at an example to better understand what this computation cache really looks like at a function level. So on the left-hand side, we have this small function foo. It takes in certain inputs, does some processing, and returns an output. The cache entry, which is on the right, which we refer to as a function signature, essentially has two components. One is the input state, which is all the state that a function accessed while executing that during its invocation. And output state is the state with the function wrote to or returned as a result of its execution. The input state is important because you use that as a criteria to decide when a particular function's cache entry can be reused, and output is the essential result of the computation, which will end up getting reused. So now let's look at the second question, which is how do we get this function level cache information? So for this, we'll have to apply some pretty old program analysis techniques. We run each of these functions through a static analyzer, which annotates all the variables inside a function and marks them and kind of categorizes them as to which ones are of interest and which ones are not. Function variables that are of interest get injected with certain instrumentation code. When the browser executes this modified version of a function, it essentially is capable of generating this signature that I showed earlier. Now let's look at the potential benefits that we can see from this client-side JavaScript execution cache. So in order to estimate the benefits, we load the same web page twice. Each set diagram here represents the set of JavaScript invocations that are executed as a result of loading the page. The benefits of using an execution cache essentially are those intersection set of functions which are deterministic, that is given the same inputs, they generate same output, and also those set of functions which did indeed see same inputs across two page loads. We accumulate their runtimes, and that essentially is the potential benefit that this computation cache will give us. So we run this experiment on 3 different corpuses of website, Alexa top 500 pages. High compute pages are those pages which took greater than 3 seconds, despite eliminating all network. And we picked 200 random pages from DMOZ, which is a directory of the web. For each of these pages, we loaded them twice at a time interval of 1 day. And then we computed that for a latter load of a page, what percentage of JavaScript execution could have been skipped by reusing the execution from the prior load, which was done a day ago. As you can see from this graph, on the median page, around 81% of the execution time for the high compute pages was possible. Since we have been focusing on client-side computation being the bottleneck, I mentioned previously that JavaScript accounts for roughly 69% of all the client-side computation that happens. So this 81% translates into a 49% savings on the total client-side computation, which translates into 990 milliseconds of raw runtime savings. So far I've been talking about how this computation cache can be reused across multiple loads of the same page. However, we wanted to explore this idea across different pages on the same site, because different pages are more likely to incorporate similar aesthetics, similar functionality, and therefore same JavaScript files. In order to conduct this experiment, we randomly sampled 10 sites from our corpus, and we choose 20 pages on each of those sites. Then we load these 200 pages at 3 different time intervals, 1 minute, 1 hour, and 1 day, and do the same experiment as before, where we try to see what percentage of JavaScript execution in a latter load of a page can be reused from a former load of a different page on the same site. Here we saw around 29% of JavaScript execution that was reusable for the median page, given a time interval of 1 minute. Finally, I'd like to talk about some of the high-level challenges that need to be overcome in order to realize this vision. There are 2 high-level challenges. One is the overheads associated with instrumentation and the overheads associated with caching. So by instrumentation overheads, I mean the overheads incurred while doing all the state access tracking. So like I mentioned, for each function, you'll have to generate a function level cache entry, which requires tracking all the state that a function reads or writes to. Doing this tracking is extremely expensive, specifically more so because we are doing this out of function granularity. Modern web pages have tens of thousands of functions that get executed during each page load. One potential solution to overcome this challenge is to leverage spare CPU cores. Since I mentioned that modern flagship smartphones have tons of CPUs, which are not directly contributing to improving page load performance, some of those could be leveraged to execute this tracking operations. The only challenge here is that these executions would have to be done in an idempotent manner, because executing JavaScript function can negatively impact either client-side state or server-side state. The next set of overheads are associated with cache management. These overheads are in terms of the lookup times, when you're anytime reading from the cache to determine whether it's a cache hit or a cache miss, and storage cost. Like I previously mentioned, modern pages have tens of thousands of JavaScript functions, and now you have a cache entry corresponding to each function. So therefore, this will naturally increase the storage cost for each web page. The potential solution here is to not really focus on all the functions that get executed on a page, but only the small fraction of performance critical functions. So in our corpus of Alexa top 500 pages, we noticed that there is this some kind of a Pareto rule where around 27% of functions actually account for 80% of the execution time. And these functions are what we annotate as performance critical function. Another good quality about these functions is that their execution time is relatively stable. So it does not vary across multiple loads. So it will not be the case that one function took seemingly high runtime during one load and it did not during a second load. In conclusion, I briefly talked about how there has been a shifting trend from network to computation being a bottleneck, specifically client-side computation. I summarized some of the prior work in this space and talked about why it is hard or what is hard about or what are the factors that are hindering its adoption. And finally, I talked about our proposal of a purely client-side solution, which is based on a JavaScript computation cache and the significant potential it has on some of the legacy pages. With that, I'd like to conclude my talk.